Hello, everyone. Thank you for joining our session today, the Snack and Learn webinar. I would just like to mention the housekeeping items. The presentation slides are available to download in the Material tab as a PDF, and also there will be time for question and answers if you can please log your questions in the question tab on the top right. I would hand it over to Bertil and Andreas to start the presentation. Thank you.
Thank you, Sharon, and welcome to this Snack and Learn webinar. It's about IoT for groundwater level visualization and optimization in pump and treat remediation facilities. My name is Bertil Carlson, and me and my colleague Andreas will be your host in the next half hour. So we welcome to all of you, wherever you are in the world. Andreas and I work in the Danish office in the city Tostrup. It's not far from Copenhagen, the capital in Denmark. And we work in the Department for Soil and Groundwater Pollution. The agenda for this presentation: first, what is IoT and what is pump and treat remediation? Then some information about the client, the capital region with whom we carried out this development project. Then some background information about pump and treat plants in the capital region, followed by explanation of our idea. Then I have some information about the test site where there's heavy groundwater contamination. And then Andreas will talk about implementation of the system and the data flow, also the results and conclusions, and then some perspective. Well, what is IoT, Internet of Things? You can say it's a network of connected devices that facilitates communication, and there's plenty of examples. It could be smartwatch home security systems, it could be smart speaker system or glucose monitoring for diabetes. There's a number of possibilities, and often sensors are used because it's very good for monitoring purposes. What is pump and treat? In Denmark, we use groundwater for drinking water. We have a high population density in Denmark, and in some areas, the waterworks are not far from industrial districts. Therefore, groundwater plumes often poses a risk. Cutting off groundwater plumes to prevent spread of pollution performed by pumping wells established in the outskirts of the plumes, and where the pumped water is purified on a water treatment plant, that's called pump and treat. And the water treatment, it could be on carbon filters, it could also be other kinds of water treatment. And then the purified water is let out to a stream or lake or something like that. And it has to keep on pumping to prevent spreading of this plume. And many of these pump and treat facilities are established in the 80s and in the 90s. And we anticipate that a number of these plants pump more water than actually necessary. When we practiced this presentation with Sharon from Global, she said it would be a good idea to have some fun fact. And I do have some fun fact about this remediation technology, because actually you can sing it. Yes, you can. It goes like this: pump up the jam, pump it up while your feet are stumping. I hope you're smiling out there. And now that you have this old technotronic hit on your brain, I will move on to the next slide. Some information about the client. Here you see Region Hovedstaden. It means the capital region with whom we carried out this development project. Denmark is divided into 5 different regions, and their main task is to manage the healthcare system in Denmark. But also they have a task related to soil and groundwater pollution. If the pollution occurred before the year 2000, the region must investigate and clean up on these sites. If the pollution occurred after 2000, when the Soil Pollution Act was adopted, then it would be the polluter, the company, who has to pay. The capital region receives about 160 million Danish crowns a year from the state. Is about 24 million US dollar. And a big amount of this is allocated to advanced investigation, cleanups, and operation of remedial facilities. Also, sometimes the government allocates extra funds for cleaning up the very huge contaminations. In the capital region, there's 59 active pump and treat plants, and the total volume of extracted water is around 2.4 million cubic meters. So that's about 41,000 cubic meters per pump and treat plant, and that corresponds to 4.7 cubic meter per hour. This figure, it shows the age of the plants. For instance, if you look at the column with the number 7, it means that 7 plants were established 29 years ago. That's in 1995. So a lot of these plants were established in the 80s and 90s. And we believe that many of the plants must be in operation for 40, 50 years, maybe even longer. That means a large consumption of electricity and carbon from carbon filters, and also a large carbon dioxide footprint. And that's why it's interesting to look at these pumping rates. Because it's important not to pump with too high rates, thus this unnecessarily high energy consumption. Conversely, pumping rates should not be too low either, as hydraulic fixation of the groundwater contamination must be ensured. So the idea was adaptation and modification of an existing process to determine this pump rates and use automation of an 2D analytical model and use IoT for visualization, calibration, and verification. And in a little while, Andreas will present more technical details about this system. I just have a few information about the test site. The test site is in the city Birkerød in the capital region, and the pollution is with the chlorinated solvents. There was previously a metal factory on this property, and chlorinated solvents, trichloroethylene, was used for degreasing metal objects, and there's a heavy contamination. Some years ago, there was a thermal purification of the upper soil layers, but also there's a heavy groundwater plume, and therefore pump and treat was established in the outskirt of this plume. On this figure, you see the horizontal distribution of the contamination. And this figure shows the vertical distribution in the groundwater. And it was a good test site to use for the development project because it was simple geology. We had one aquifer with sandy soil. We could view it as a 2D problem, and we did have good data about the wells and the aquifer properties. The pumping wells, there were 2 wells in the pump, each with 3 cubic meters per hour. That's in total 6 cubic meter per hour. And we had a suspicion it was too much, not necessary to pump with these pumping rates. So now I would like to give the word to Andreas.
Thank you. So the system that we implemented, how does it look? This is a flowchart that shows how the system was set up. So first, we took all of the IoT loggers and we installed them inside of the monitoring and the extraction wells. Then we had this 2D analytical hydrological model where we inputted all the data about the pumping wells and the well construction, the aquifer properties, And then we took a desired capture radius and used to for the model to use for a goal for the optimization for the model to run. All this IoT data is then transformed into a grid for the natural water table, and that will be used inside of the 2D analytical model as the base scenario. Then the program will automatically determine the needed pumping rate for the remediation for it just to have the desired capture radius that we defined. Then the pumping rates are implemented for the pump and treat facility, and then all the IoT data is then transformed into an operational water table, where we can visualize the water table on WSP's web portal. And then we'll compare the observed water table with the modeled water table and see if they look like each other. And if the measured water table does not resemble the modeled water table, then we will use some new hydrogeological parameters, and the model will run again for another loop for us to get the correct all the correct data inside of the model. So the IoT sensors here, we can see them. They are just sensors with a modem on top. They are ventilated. So they're ventilated because they needed a barometric compensation for the change in atmospheric pressure. And all the data from these sensors is then delivered to WSP's web portal, as I mentioned earlier. It's called Vandportalen or Water Portal. And here it's delivered for visualization and data management. And before the sensors are calibrated, then all the wells are leveled out digitally to get the maximum precision for the wells. Then the wells are sounded, and the sounding is being used for the calibration of the IoT sensors. Here we can see the natural water table. It's interpolated from the data from the IoT sensors. It is shown as an isopotential map, and we can see there's a natural flow here from west to east towards the extraction wells. So that's kind of lucky. The natural water table here is used as the baseline scenario, and that's for the analytical model to use. So we will determine a grid size for the model, and that is determined based on the desired quality of the model and the amount of data we have available. So we have to determine the required capture zone. Here it's shown as the yellow particles. So that is defined as what we need to capture. And one particle is placed inside of each of one of the cells along the line of the required capture zone. So then the optimal scenario can be found, and it will be found as the lowest pump rate to capture all of the placed particles along the capture radius. So here is what the 2D analytical model looks like. It's actually just an Excel sheet that is automated with macros, and for this project is automated, and the 2D model is a WSP developed model, so it's actually free to use for any WSP employees. All the data about the aquifer and the wells are then inserted into the model, and then the model will run for different scenarios, and the scenarios will be for each of the extraction wells, the 2 extraction wells. They will run for between 0 and 5 cubic meters per hour each. And this will lead into a total of 441 different scenarios. If we would just have the 3 extraction wells, then it will equal 9,261 different scenarios. But each of these 441 scenarios generate a grid file with all the results, and that is automatically run through a particle simulation, a forward particle simulation, where it will save all the particles and it will save data about the capture percentage for the desired capture radius that we defined earlier. So here's what it looks like. This is a visualization of the forward particle simulation. We can see that all the particles that end up in the extraction wells, these are the extraction wells, uh, if they're defined as captured, then they're visualized as green. If when they're not captured, they are visualized as red, and that's because they're not ending up inside of the extraction wells. So the amount of the predefined particles that are captured is then logged as the capture percentage. Here we can see that the green goes further than the yellow capture radius, so that's more than 100%. It's 100% at least. And we will only look at the scenarios that have a capture radius of 100% to be considered as the optimal scenario, because we want all the particles to be captured. And then the scenario that captures 100% of the capture radius, but with the lowest pumping rate, will then be considered the optimal scenario. So here, this is the theoretical grid. That's one of the theoretical grids, one of the 441 different ones, and it's visualized as isopotential map. It's visualized as a grid file, and we got the grid file through interpolation. And since the calculation is theoretical, then all the individual cells will be correctly affected because of the computation inside. And it's very hard to compare the theoretical isopotential map with the data from the IoT, because the observed data points will only be a few measurement points, and the observed map is then created with interpolation. It will not look like the theoretical one. So if we look at the theoretical one, here we can see all the red dots are the measurings from the observation wells, and the observed water level is then visualized through the interpolation. And as we can see, it doesn't look like the theoretical one. But we also use the level from the extraction wells, and we can do that because they are compensated for the resistance in the screens and in the pumps. And the compensation happens with the use of the efficiency, and we find that during a multi-well pumping test. And the effectivity of the well is defined as the percentual difference between the observed and the theoretical drawdown at the outer well parameter. But how can we compare them then? If we look at this is only the points from the theoretical drawdown at the same points from the observations points, and then it's interpolated. So if we only use the observation points to compare with the theoretical ones, we can actually use it for calibration purposes and validation. And the difference in each of the points is used for the calibration. So we can change the transmissivity inside of the model and see how big the difference is between the observed and the theoretical one, and either validate input or try a new data point and run the model again. So here we can see that we changed the transmissivity. It's along the x-axis here, it's the transmissivity, and we got two different y-axes. We got the sum of the error in all of the observation points, and we got the maximum error in just all of the observation points. So the maximum of the error. So we can see when we change the transmissivity, we want the lowest sum of error, but also the lowest maximum error for the model. So we can see we actually had to change the transmissivity with a 20% increase. So when we integrated that into the model, then it could run again, and we could get some results. So when the calibrated transmissivity is integrated into the model and then validated, we will get an optimization matrix. And that is generated for all of the different pumping scenarios. We can see here it shows the capture percentage. So we will only consider the green ones, which is 100%. So here we can also see the two different wells, the extraction wells, and the different scenarios with how much the pumping rate is. So for us to get the optimum scenario, then we want the lowest possible sum of pumping, but also the lowest possible pumping for each of the extraction wells. So we need to rank it to get the optimal scenario. So here is all the different scenarios ranked. So we wanted the lowest sum, but also the lowest maximum scenario, the lowest maximum pumping rate for each of the wells. So we can see we have 4 scenarios with a sum of pumping of 2.5 cubic meters per hour. We know that before it was 3 and 3 cubic meters per hour. So now we can go all the way down to 1.5 and 1 cubic meter per hour. So that's more than a 50% reduction. But we can also see if we want the 2 extraction wells to pump more equally, then we would actually go up to 2.75 cubic meters per hour and pump 1.5 and 1.25 cubic meters per hour. So the optimal scenario for this one would be 1.5 cubic meter per hour and 1 cubic meter per hour for the 2 extraction wells. So to sum it all up, we are actually able to decrease the pumping rates with more than 50% and still be able to capture all of the predefined contamination. And we found that the 50% decrease in pumping rates did not actually equal a 50% decrease in electricity. And that is due to the pump function for the specific pumps. For this pump, because it's a fairly large pump, the decrease in 50% only yielded a 20% decrease in electricity. But we intend to switch the pump so we can obtain the full savings due to the optimization that we found. We also know that if we decrease the pumping, uh, then we will lower the pumping of the non-contaminated water, and that will lead to higher concentrations and thereby prolong the lifespan of the activated carbon filters. And the activated carbon filters are actually the ones with the highest carbon footprint because it takes one it takes just for 1 kilogram of activated carbon to be produced, it will release 7 kilograms of CO2 equivalent, and the destruction of just 1 kilogram will release 2 kilograms of CO2 equivalents. So IoT, it's here to stay, so we need to utilize it, and we need it to help us in future projects. And IoT, it can be used for many different cases. Like here, we did with theoretical modeling. We validated the model through real-world data, and it was delivered with sensors with IoT. So it can be used as a quick way of visualization of real-world data and its derivatives. And with the sensors that we used, it's possible to use it for visualization of pumping tests, or you can use it for the generation of isopotential maps. But IoT can also be used for early warning systems for floodings, monitoring, doing dewatering in construction. There's almost no limitations for the use of sensors. You could also use electric conductivity, for example, to investigate for salinity. You could use temperature for measuring the groundwater influx in surface water. You could use oxygen, or you could install tampering alerts for different devices. There's almost no limitations. So IoT is definitely very nice to use, and it's here to stay. So we need to utilize it. So now I will open up for any questions.
Thank you, Andreas and Bertil. Fantastic presentation. I will mention again the housekeeping items before we move to the Q&A. The presentation slides are available to download in the Materials tab on the top right of this platform, and also please continue to log your questions in the question box. I will start with the first question. What are the biggest limitations when using this method for optimization?
Yeah, I can start with that. we have some limitations because, of course, it's a 2D model, so you need the conditions to be correct, and also you you need the data to be able to run the optimization. So you need the data beforehand. So you need some data about the aquifer, you need some data about the different wells, and you need yeah, the data, and also the amount of data points. So if you want, you could have a lot of data points just to be sure about the optimization. If we looked at the earlier ones with the theoretical isopotential map and compared it to the observed one, we could see a very big difference. So if we wanted to just use the observed one for particle simulations, for example, then it will have some big gaps. We also have some problems with yeah, the what is it called, the effect of the drillings, the wells. It will change over time, so you also need to have that parameter in mind.
Thank you. Are there any limitation of the model being as 2D?
Yeah, again, because it's a 2D model, then we will just assume that everything will only be flowing in the horizontal space. There will be no vertical transportation, and all screen placements are assumed to be in the optimal space. So when you are pumping, then you'll just assume that everything is always horizontal, and everything inside of the aquifer is assumed to be homogeneous and heterogeneous, and just flow directly to the screen.
Thank you. Could you share with us what platform do you use for the IoT visualization?
Yeah, the platform that we use is called Vandportalen. It's the water portal. It's again a WSP product, so it's a GIS platform that is based on Google Maps, and all the IoT data is then visualized on the GIS map inside of the water portal, and it will show both the time series and will show the overlays like shapes and isopotential maps as well.
Thank you. I will take the last question, and all additional questions will be answered directly by the presenters. Can this system be used when you're removing groundwater during tunneling or mass excavation?
Yes, the system can be used in projects where it's necessary to carry out groundwater level lowering. Maybe the part about particle tracking would not be necessary, but the system with loggers sending data continuously to a platform, that would be very good to have. I can say we are still working on improving different things. For example, in this development project we had with the capital region, it was necessary to remove the covers on the monitoring wells. The covers are typically metal covers or concrete covers in order to send data. In many places, this will not be possible if the wells are located in road areas or car parks, or places where there can be theft or vandalism. And therefore, we are currently testing and developing methods to equipment to be able to send data with covers on the wells, so that the covers can remain on the wells in future projects.
Fantastic. Thank you. Thank you, Andreas and Bertil, for your presentation. It's nice to convey a very technical presentation, even with a smile. So thank you for that. And thank you all for joining us today. We will wrap up the session now. Please feel free to reach out to the presenters via the contact data that are shown on the screen for any additional questions. So again, thanks everyone, and have a wonderful day. Thank you so much.